ME204, Relative Motion Analysis of Particles. Have you ever been on an airplane and looked out the window and watched another airplane go by? Here's a video that I took when I was recently on an airplane traveling to Arizona. As I looked out the window, I saw another airplane going another direction. It looked like that airplane was going very fast. Relative motion is the motion of an object relative or from the perspective of another object. From my perspective, the other plane was moving very quickly. However, would it look the same from someone who is watching the planes from the ground? It all depends on the viewer's perspective and is relative to their own motion. Here's an example with a school bus. There's a long aisle that goes down the middle of the bus, and students will move back and forth from seat to seat and walk down the aisle. Let's say we have a bus that's traveling at 55 miles per hour. There's a boy running down the aisle at 5 miles per hour. How fast is the boy moving? Well, intuitively, we could figure out that the boy is moving 60 miles an hour. The bus is going 55, he's going another 5, so his total speed is 60 miles an hour. So let's write an equation for what we did intuitively in our minds. If the bus is A and the boy is B, then the actual velocity of the boy, VB, is equal to the actual velocity of the bus, VA, plus the velocity of the boy relative to the bus. From someone sitting on the seat in the bus, the boy is only going 5 miles an hour. That's his relative motion. His actual motion, from someone standing on the curb watching the bus go by, is his relative motion plus the speed of the bus. You can rearrange this equation to look like this, so that the velocity of the boy relative to the bus is equal to the velocity of the boy minus the velocity of the bus. Or VB with respect to A is equal to VB minus VA. An easy way to remember this is think of the letters BA, BA, and they go in that order, ba, ba, or AB, AB. So from this discussion, is this the boy's actual or his relative velocity? It's his relative velocity, because it's his velocity relative to the bus. Have you been on an airport moving walkway, where the walkway moves along and you just stand and it takes you to where you want to go? Sometimes I'll take my kids to the airport, and if the walkway's moving 5 feet per second, and my son decides to walk the other way at 5 feet per second, how fast is he actually moving? Well, he's going 0 feet per second like he would on a treadmill. So let's write an equation for what we did intuitively in our mind. The walkway is A. My son is B. So my son's actual velocity is equal to the velocity of the walkway, 5 feet per second, plus the velocity of my son relative to the walkway, which is 5 feet per second, but it's in the negative direction. So it's 5 feet per second minus 5 feet per second, which equals 0. Is this 5 feet per second his actual or relative velocity? This would be his relative velocity, because he's walking 5 feet per second relative to the moving walkway. Let's look at a relative position example, using positions instead of velocities. The green boat is in trouble. We have a spotter who's in the lighthouse, and he's watching this green boat, and he determines that the location of the green boat from his perspective, from where he's sitting, can be represented by a position vector, r sub g, equals 4I plus 8j. The spotter radios the yellow boat, which they know is located at a position ry is equal to 6I plus 2j, and asks them to go to the rescue. We want to find out what's the position of the green boat relative to the yellow boat. How far are they going to have to travel to rescue the people in the green boat? Well, if we use the same type of equation, where we said BA, BA, or the position of the green boat relative to the yellow boat is equal to the position of the green boat minus the position of the yellow boat. We know what the position of the green boat is, and we know the position of the yellow boat. Now we can't just subtract these directly, so let's put them in their respective components. So the position of the green boat relative to the yellow boat is equal to 4 minus 6I plus 8 minus 2j. Solving this, the position of the green boat with respect to the yellow boat, or from the perspective of the yellow boat, is equal to minus 2I plus 6j. And if we draw that out, the yellow boat goes minus 2 in the x direction and a positive 6 in the j direction, or in the y direction. Then we have the vector that represents the position of the green boat from the perspective of the yellow boat. So relative position, velocity, and acceleration can all be related to each other, and they're related by their time derivatives. We know from the last example that we can represent a relative position as the difference between two vectors. Or, rewriting that and collecting the terms that are in the same direction, we have this equation. RA with respect to B is equal to RA minus RB in the I direction plus RA minus RB in the j direction, where R is a position. If we take the time derivative of that, then we get that the velocity of A with respect to B is equal to the velocity of A minus the velocity of B in the I direction, plus the velocity of A minus the velocity of B in the j direction. And we can represent that graphically as well. If we take the time derivative again, then we get that the acceleration of A from the perspective of B is equal to the acceleration of A minus the acceleration of B in the I direction, plus the acceleration of A minus the acceleration of B in the j direction. And again, this can also be represented graphically. To represent these graphically, we simply draw each vector from its tail at the same starting point. And then depending on what we're looking for, if we want, for example, A from the perspective of B, we start at B and draw it towards A so that we get the correct direction. There are a couple of methods that we can use to solve these problems. First, we can use vectors just like we've been doing. We use vector math, addition or subtraction, to solve the problem. The second method to solve these problems is using a graphical method. This uses the lengths and the angles with the law of cosines and the law of sines to solve the problem. As a reminder, the law of sines is as follows. If we've got a triangle with lengths A, B, and C, and angles alpha, beta, and gamma, where alpha is opposite of the side A, beta is opposite the side B, and gamma is opposite the side C, then side A over the sine of alpha is equal to side B over the sine of beta is equal to side C over the sine of gamma. For the law of cosines, for any side, in this case we're only going to use side C, but we could do this equation with any of the other sides as well. Side C squared is equal to side A squared plus side B squared minus 2 times AB cosine of gamma, where gamma is the angle opposite the side C. Let's look at a vector example. We have an airplane A that's traveling at 800 feet per second at an angle of 20 degrees. At the same time, we have an airplane B that's going 650 feet per second. So this is similar to the problem that we showed at the beginning when I was traveling in the airplane. We want to know what the velocity of the airplane B is relative to the plane A. To solve this using vectors, we want to use the equation VBA is equal to VB minus VA. So we need to collect the like terms, or the terms associated with their respective directions. So VBA is equal to the velocity of B minus the velocity of A in the x direction, plus the velocity of B minus the velocity of A in the y direction. So we'll need the vectors. Well, we know from looking at airplane B that the velocity of B is equal to 650 in the x direction, or in the I direction, plus 0 in the j direction. Airplane A's velocity vector is equal to minus 800 times the cosine of 20 in the I direction, plus 800 times the sine of 20 in the j direction, just breaking them into components. Now we go back to our original equation, and we've got to put the right components on the right part of the equation. So we'll put in 650 for velocity of B in the I direction, and minus 800 cosine of 20 for the velocity of A in the I direction. We'll put in 0 for the velocity of B in the j direction, and we'll put in 800 sine of 20 for the velocity of A in the j direction. Then we end up with this equation. Simplifying, we get that the velocity of B from the perspective of A is 1,402 in the I direction minus 273.6 in the j direction. Using a vector, we have everything we need to characterize this motion. We can tell what the direction is, and we know what the velocities are in each direction. However, sometimes it's convenient to see this as a magnitude and an angle. So to get the magnitude, we take the square root of the sum of the squares, which would give us 1,428 feet per second. To get the angle, we know that the tangent of an angle is equal to the opposite side over the adjacent side. In this case, it's 273 is the y component over 1,402 is the x component. Solving for theta, we get that it's traveling at an angle of 11 degrees. Let's look at this same example, but solve it graphically. In this case, we'll draw vector A, and we're going to exaggerate it a little bit and draw it a little bit longer. Vector A was 800 feet per second at an angle of 20 degrees. From the tail of vector A, we're going to draw vector B. Vector B is 650 feet per second, and it's all in the I direction. Now we need to complete our triangle. We're trying to find the velocity of B relative to A, or the velocity of B from the perspective of A. So what is A seeing? In order to see what A is seeing, we want to draw our vector from A to B, and we'll call that length C. The angle opposite of C is gamma, the angle opposite of A is alpha, and the angle opposite of B is beta. Now I have two lengths, and I have an exterior angle. I can get the interior angle gamma by simply subtracting 20 from 180. Then I can use the law of cosines to figure out what the length C is. So the law of cosine says c squared is equal to a squared plus b squared minus 2ab cosine of gamma. Plugging in what we know and solving for c, we get that c is equal to 1,428 feet per second, which is the same magnitude that we obtained in the vector example. But this only gives us a magnitude. We also need to know what the direction is. If we use the law of sines, 800 over the sine of alpha is equal to 1428 over the sine of 160, or a over the sine of alpha is equal to c over the sine of gamma. Solving for alpha, we get that alpha is equal to 11 degrees, which is the same as what we got in the vector example. That 11 degrees could be measured from a horizontal line at the tail of C clockwise. Our next topic is linear and angular kinematic relationships, rotation about a fixed axis.